So I'm really delighted to invite Rehan and Haris up to speak about their work on deploying homomorphic encryption technology at kind of billion device scale.
Thank you. Hello, everyone. My name is Rehan. I manage the machine learning cryptography and privacy group here at Apple. I'm joined by my colleague Haris. And today we will talk about how we are leveraging HE to power a bunch of different features that are running at scale on over 1 billion devices. Where we've seen a use for this stuff is there are a lot of on-device experiences that can either be enabled or enriched with information from servers. But whenever we start thinking about these features, we look at what data might potentially need to leave the device, how privacy sensitive is that data, and then how can we best design a system that protects that data's privacy. And in all these cases, homomorphic encryption is a primitive that shines through. Because of its ability to compute unencrypted data, it's able to retrieve information from a server privately. So for example, the first feature on the slide is private live caller ID, where we're able to identify real-time caller information for incoming phone calls from an index on the server to identify either registered businesses or, more importantly, spam phone numbers. And then we can notify the users, we can block the stuff on device and protect our users. And we do this in a way where the phone number is not revealed to the server. The second feature on the slide is called enhanced visual search, where we improve on-device photo search by privately tagging images for domains that are pretty hard to do just on device, such as global landmarks and places of interest from all across the world. And we'll do a deep dive into this feature to explain the system better. Finally, the third feature on the slide is categorization for email senders that are registered businesses with Apple so that we can better organize and categorize your mail. So as you can see, there are a bunch of features that can use this information from servers to improve the experiences on device. Now, we need to do this in a way where we have a formal Apple privacy commitment where any data that leaves your device, any client queries, they remain private even from Apple. However, we need to do this in realistic, practical constraints. Because we have such a large device population, we're probably hitting tens of thousands of queries per second. So there's really high throughput. And then the communication cost for each of these queries should also be within, let's say, less than 1 megabyte. And on the client side, we need to be enabling these features where the client storage per feature is relatively cheap. And we need to build this in a way where the user experience is high quality. So we need exposure to all the information we can from the server. So to better explain the system, let's do a feature walkthrough through enhanced visual search. As I mentioned, we're improving on-device search for domains that are really difficult to classify with just an on-device solution, like landmarks and places of interest. And so imagine you've gone on a holiday, maybe even this conference here, and you've taken lots of photos. And you want to be able to recognize these photos and search for them at a future point in time. And so before this feature, let's say we want to search for the Chapel Bridge, the picture in the middle. And so before this feature, how you would go about doing this is you would search for a generic class, let's say monument or bridge, right? Or possibly a location where this was taken, let's say Lucerne, or a neighborhood in Lucerne when this was taken. And you would get many search results, and then you'd have to scroll through them, and you would get to the photo that you wanted. And we termed this as poor search recall because the actual result was much further down in the list, all right? And so we can improve this experience if we could tag this image with the exact location that was needed, and then you get all the search results as you see right on the top of your screen. So how do we begin? Let's say we have this image where there is a landmark in it. The next, there's an on-device machine learning model that scans through this image and detects a region of interest with a potential landmark. There's another machine learning model that runs only over this region of interest and says, OK, there's this landmark. I'm going to convert this into something called an embedding. And let's zoom into what this embedding is, because this is going to be the primary computation for our HE compute. So simply put, an embedding is generated by a machine learning model, and it's a float vector of fixed dimension. But the special property here is that it maintains some semantic meaning about the input, and it does this in a way where similar-looking images are closer together in this embedding space, and dissimilar images are further apart. And so we can compute the similarity with a bunch of different metrics. The one that is sufficient for our workflow is just a simple dot product. And so here's a setting. You have this query embedding for the input image, and then you've generated an embedding for each entry in the index. And so you just take this embedding, you take all the embeddings from the index, you compute the similarity score, and you tag the label for the maximum score from the index back to the input image. Okay, and so in this case, Chapel Bridge is the second embedding, and so you take that, and then you label the input image with the label associated with that entry. So there's a trivial approach, which is perfectly privacy preserving. You take this entire index, and you download it down to the device, and then you're going to be processing all these queries completely on device, right? And then you have the tags available. You can put that next to the image, and they are available for search. Perfectly fine. And this is encouraged for small databases. But the domains that we are interested in is where these indexes can go from 5 million or like single-digit million to tens or hundreds of millions of entries. And what that means is just to power one feature for one domain, you would potentially need to sync gigabytes or tens or hundreds of gigabytes of data. Additionally, the embedding itself is probably not enough to make a decision. For example, there can be temples that look quite similar to each other. There can be bridges that look quite similar to each other. And in these cases, you need additional signals like the location of the entry in the index, a popularity score probably for something that's more popular, the locale where it's present. And all of this means you have additional metadata per entry, which is some number of bytes per entry. And so again, the database size grows prohibitively. Finally, these databases are dynamic. You can have new entries, you can delete entries, you can update the names of places, et cetera. And so syncing all these changes to over 1 billion devices is operationally very challenging. And so we do realize that we need to send this embedding off the device to power this feature. Because in this trivial approach, yes, we are definitely meeting our privacy commitment. We are meeting server constraints because you're just syncing the stuff once on device. However, we're not meeting our client constraints of a small storage and this high quality user experience. So in a setting where this needs to be sent to the server, what are you doing? You're converting this embedding, sending it to the server, you're computing this dot product server side, and you're syncing the label back down to the device, all right? And the question is, why is there a privacy issue here? You're just sending this embedding, you're not sending actual photos data. However, there's been a lot of work where there are a lot of efficient reconstruction attacks that suggest that just from the embedding, you're able to recover almost all of the input data. And so we do really need to protect this. This is very privacy sensitive. So one candidate approach is you can just use HE directly. What do? You encrypt this embedding with a secret key that stays on the device, send this encrypted embedding to the server, compute all these scores in the ciphertext space, and then you get all these scores down to the device where you decrypt them and you select the maximum score. Great, this is possible. And one of the state-of-the-art approaches that did this when we were putting out the system is called Tiptoe, which is, it does this relatively efficiently for an HE scheme. It offers full query obliviousness for privacy. And yeah, it's a great system. However, it falls short of our practical constraints, where we need to serve tens of thousands of queries per second. More critically, the communication cost for this scheme is around 17 megabytes per query. And so it's prohibitively expensive from a server point of view, but also from the client. You're generating 17 megabytes of communication for each query. For each feature, you can have tens or hundreds of queries. And so the cost on an iPhone is really, really high. And so that's where this becomes impractical. And so we need to think about this maybe slightly differently. And yes, it maintains Apple's privacy commitment. It maintains some of the practical system requirements, especially on the client where there's a small storage. And there is a high quality experience because you have access to the whole database. But like I mentioned, it's falling short of our server constraints. So we know there are two problems. We know there's this high computation problem, and we know that there's this high communication problem. And we solve this in two different ways. We use differential privacy to access some subset of the whole index. So that helps with our computation cost. And then we also leverage some cool optimizations in our HE scheme, which help with the communication cost. To cover both of these, I'm going to hand it over to Harris.
Thank you, Rehan. So as Rehan said, we propose two-step solution. Let's look at how we reduce the server computation by using differential privacy first. At the setup stage, the server used the standard machine learning technique of clustering to first divide the entire index into the clusters. Then, at the time of the query, let's look at this simpler protocol. The client is only going to find the nearest cluster, send that, and the client can do it just by using the centroid sent by the server. Client is going to send this centroid to the server, and server's response is just the entire cluster back to the client. So note that this scheme already improves over the previous scheme where the client was sending the embedding. However, it still doesn't provide a strong privacy guarantee because the server is learning the nearest cluster. And just by learning the nearest cluster, the server might be able to know some information about the client query. For example, here, if the server knows that the client query falls in cluster C2, it may learn that the query is something about the bridges. So we want to suppress that information. So now we have another problem. We get rid of the embedding, but now we have a problem that the centroid, the cluster themselves reveal information to the server. We have this observation that in a large scale system, something like at the scale of Apple, there are many users are making the queries at the same time anyway. So we can try to hide the client's clusters, which is a query, into the query batch of queries made by the other clients. So in other words, we propose a scheme which trade off efficiency for privacy, which provides a worst case privacy leakage through clusters, and which guarantees epsilon delta differential privacy at a user level with respect to user's entire photo library. So before I go into the details of this protocol, let me explain to you that how the intuition of the privacy provided by our scheme. Let's imagine two worlds, one on the left, where many users are making the queries to the server, and one on the right, where a particular user may not be making the query to the server. And the privacy guarantee provided by our scheme is such that the view of the server in both these worlds are similar. In other words, the view of the server's advantage in inferring the client's query, whether the client participates in a protocol or not, is bounded by e raised to power epsilon. And we selected epsilon equal to 0.8 and delta equal to 10 raised to power -9, which is quite stronger guarantee. Okay, now let's look at how we achieve this privacy guarantee. So our protocol consists of 4 steps. First, we assume that the protocol is going to run in an epoch. Every epoch, many clients are going to make a query. Second, we require anonymization. So for this, we require all the client queries go to the server through the anonymization network. We specifically use oblivious HTTP, which removes the identifiable information such as IP addresses from the client queries. Now note that even though we have anonymized the queries, but server can still might be able to link a particular query to a client. For example, if server knows a particular cluster can be accessed by a certain demographic, just by observing that that cluster has been accessed, server might be able to decipher the identity of these queries. So we require additionally each client to make certain number of fake queries. Every client is going to sample number of fake queries it is supposed to be making through a negative binomial distribution. Note that adding more fake queries improves the privacy, but we were able to find a sweet spot which does not affect too much performance. Concretely, for every real query, every client is required to make 1 or 2 fake queries only. And making a fake query is very easy. All client has to do is pick a random cluster and send it to the server. Another potential leakage can be through the timing channel. So for example, certain clients may be making the queries always in the start. That will reveal to the server who are these clients. So we want to suppress that leakage as well. For that, we require every client to pick a random slot or a random instance within an epoch for a real and fake queries, and only make the requests on that random instances. Note that for many online use cases, this may not be ideal, but for the offline use cases, such as photo tagging here, this is okay because they are delay tolerant applications anyway. Okay, so in the paper, we have already uploaded the paper, which gives the proof that by following these steps, it guarantees epsilon delta differential privacy. Here, I would like to give a little bit high-level intuition of the proof. First, we show that the server's view in a single epoch is basically a noisy histogram of clusters. Then we show that the noisy histogram provides epsilon delta differential privacy in a central model where a single curator is talking to the server. And then we show that malicious server gains no extra advantage in a distributed model where many clients are making their queries to the server. So this is for a single epoch. And then we calculated the total privacy by using the advanced composition theorem for across all the epochs a user is going to participate. Okay, so this scheme is good, that it protects the privacy, but many of you might have already noticed that it has a problem, which is that the server responses the entire cluster. This is fine for small clusters, but for the larger clusters, note that this response has become prohibitively high. So we want to compress that. To do that, we use HE. Let's quickly go over that. At a high level, for any real or fake queries, now client is going to send encrypted embedding, which is encrypted under HE to the server in every query. For this, we use BFV HE scheme, which supports ciphertext vector operations. Okay, so client is going to send that query to the server. Server will compute the encrypted scores and send all the encrypted scores back to the client. Note that because of our use of efficient packing scheme, all the scores, we were able to pack them into a single BFE ciphertext. So our response is only a single BFE ciphertext. Okay. We further use many other HE optimization. Here I'm going to touch few of them. But to understand that, we have to look at under the hood of HE ciphertext that we have implemented. In our implementation of BFV, each ciphertext consists of 2 RNS lim. If you zoom into the single slot of a ciphertext, you notice that the scores are at the higher order bits, noise is at the lower order bits. So in other words, useful material is in the higher order bits. So first we use a standard technique of modulus reduction, which allows us to get rid of one of the RNS lim in the response ciphertext. Then we further drop the least significant bits of the remaining lim. Note that dropping these bits does not affect the security of the ciphertext at all. However, it introduces some kind of decryption error, but we carefully monitor this decryption error and only drop the bits when the decryption error is almost negligible. Okay. We also did some other optimizations. Due to the lack of time, I'm only going to touch 2 more. First is we improved the server compute by realizing that a lot of this BFE operations requires modulus reductions repeatedly. So we don't have to do modulus reduction after each operation. We always allocate a slightly larger buffer and only do the modulus reduction after the buffer overflows. And the second optimization is we propose a plaintext RNS to reduce the size of evaluation key. Note that every BFV ciphertext or a computation requires client's evaluation key to be present at the server. In normal HE computation, this is fine because server can just store it and can reuse it for all the computation. However, in DP, we require anonymity, so which means that the client has to create a fresh evaluation key and send it freshly with every real or fake queries. So evaluation key is basically the communication bottleneck. So by using RNS, plaintext RNS technique, we were able to reduce the size of evaluation key by around 4x. Okay, so here are some exciting results which we were able to achieve by combining HEDP anonymization network. The first thing is that we were able to achieve a QPS of more than 25,000, and our communication is only 0.5 megabyte. So in other words, we were able to achieve significantly better performance than what we would have been if we only use HE. So now to wrap up my talk, before going to wrap up this talk, you can see that all our proposed approach does provide a standard guarantee of privacy, and it nicely meets both of the client and server constraints. Now, to wrap up our talk, I'm going to hand over back to Rehan. Thank you.
All right, thanks, Haris. So all the optimizations that Haris talked about, they are open sourced for our server implementation on Apple's GitHub as part of Swift homomorphic encryption. And so it's auditable. These contain all our optimizations, and feedback is absolutely welcome through GitHub. Similarly, on the client side, all our code lives inside Core Crypto. And again, that means it's auditable. It includes all these optimizations, and it's available at developer.apple.com/security. So to summarize this talk, we have been using HE to enhance on-device experiences that would not be possible without it, with information from the server, and there's a real need for this on Apple platforms. We are able to do this in a way where we're leveraging HE, combining it with other technologies, and we're able to deploy this for several features at scale, right? On over 1 billion devices. And the important takeaway is that maybe HE itself is not enough. You need to combine this with other privacy technologies that are available in our toolkit. It could be differential privacy, it could be anonymization networks. One thing we didn't talk about here, but we leverage this, in our private live caller ID solution is we also use privacy pass for anonymous tokens. And so we need to take all these technologies that we have available, combine them into an end-to-end system that can deliver privacy for our users. Now, we have a bunch of public documentation and resources that goes into everything that we talked about. Like I mentioned, our code lives on Apple's GitHub. There's a high-level overview in a blog post that's available that talks about all the features I just mentioned. The proofs are in our technical paper. And because caller ID is available for third-party developers to integrate as well, there are some developer docs on how they can incorporate this into their apps. And with that, yep, thank you.
So maybe I have time for one quick question while Christian comes up to set up.
Thank you for the very nice talk. I have a question. Are embeddings composed of floating point numbers? And what did you do? Well, how did you deal with that?
Embeddings are composed of floating point numbers. Like I mentioned, it's this like fixed dimension of these numbers that plays very nicely with other machine learning models. And I think your question is, how are we using that within HE? Like, how are we dealing with the issue that they're floating point numbers? You want to talk about how we convert them?
Yeah, so we realized that we did experimented with the efficiency and see, we realized that if you keep like the few bits, like rather than the whole floating point, if you scale the embeddings to few bits, that's sufficient enough to retain the performance. So for example, we keep to 4 to 8 bits for each.
Did you consider to use different schemes like CKKS?
Yeah, definitely we are considering that. However, note that there are, as Rehan mentioned, there are several use cases within Apple we are using at the moment, and we figure out that BFE was suitable for most of these use cases. But yeah, definitely we are looking at CKKS.
Thank you.
All right, let's thank the speakers again.